What if the universe had a voice? If you could tune a celestial radio not to the gentle hiss of the cosmic background, but to the raw, violent screams of matter being torn apart, what would you hear? For most of human history, our perception of the cosmos was a silent film, a majestic but mute tapestry of light painted across the void. We gazed through lenses capturing the serene waltz of galaxies and the steady burn of distant suns, all in the familiar, comforting wavelengths our eyes evolved to see. The universe we knew was one of profound, overwhelming silence. It was beautiful, but it was quiet. Then, in the middle of the 20th century, we taught ourselves to listen. We built new senses, electronic eyes that could perceive the hidden universe, the one painted in colors of radiation far beyond our biological limits. We opened a window onto the high-energy cosmos, a realm of invisible light of gamma rays and X-rays, expecting to find a faint ethereal glow. What we found instead in the early 1960 seconds was not a whisper but a shriek, a point of incandescent fury blazing in the sky, with the energy of 1,000 suns yet completely invisible to any telescope on Earth. This is the story of that discovery, the story of the first clue that our silent film was in fact a cosmic horror story. It is the story of a monster hiding in plain sight, a predator we could only hear, never see. It begins in the heart of the Swan in the constellation Cygnus. To understand the shock of this discovery, you have to place yourself in that era. The Cold War was at its zenith, a time of profound anxiety and astonishing technological ambition. The sky above was not just a canvas for astronomers, it was a new frontier for surveillance, a potential battlefield. The very same rocket technology that lofted scientific instruments was being perfected to deliver nuclear warheads. It was in this tense atmosphere that a small team of pioneering scientists, led by Riccardo Giacconi, aimed to do something revolutionary. They wanted to see the universe in X-rays. This was a monumental challenge. Earth's atmosphere, our protective blanket, is conveniently opaque to these high-energy photons. To see the X-ray sky, you had to get above it. There were no space telescopes, no Hubble, no Chandra X-ray observatory. The tools were primitive, almost brutal in their simplicity. They used sounding rockets, little more than enhanced military surplus, launched from the New Mexico desert. These were not missions of years or even days. They were frantic, fleeting moments of pure discovery. An aerobee rocket would scream upwards, tearing through the air on a pillar of fire, carrying a precious, delicate payload. For a breathtaking 6 minutes, it would coast above the bulk of the atmosphere, its Geiger counters frantically scanning the sky before the entire apparatus came crashing back down to Earth. 6 minutes to glimpse a completely unknown universe. It was like trying to photograph a sprawling dark landscape with a single ultra-fast flash of a camera. The initial goal was modest, almost mundane. The team hoped to see X-rays reflecting off the surface of the moon, bathed in the X-ray light of our own Sunday. It was a reasonable, safe hypothesis. They pointed their detectors at our lunar companion and held their breath. The data that streamed back was a puzzle. There were no X-rays from the moon. None. The primary mission was a failure, but as the rocket spun, its detectors swept across the rest of the sky, and something utterly unexpected happened. The instruments went wild. A torrent of X-rays, a veritable blast furnace of high-energy radiation, was pouring out of a region in the constellation Scorpius. It was the brightest object in the X-ray sky aside from the Sun itself. They named it Cygnus X-1. It was the first extrasolar X-ray source ever detected, a discovery that would win Giacconi the Nobel Prize and birth the entire field of X-ray astronomy. But it was what they found next that would truly shatter our understanding of physics. In a subsequent flight in 1964, another rocket, another precious few minutes above the world, swept its gaze across the summer triangle. And there, nestled in the wings of Cygnus the Swan, the Geiger counters screamed again. A second source almost as bright, just as perplexing. They labelled it with the simple nomenclature of the era Cygnus X-1, the first X-ray source in Cygnus. At first, it was just another data point in a brand new catalogue of cosmic curiosities. But as they refined their instruments and launched more rockets, a disturbing picture began to emerge. Cygnus X-1 was not like other stars. It wasn't even like Scorpius X-1. It was violent, unstable. Normal stars, even incredibly hot and massive ones, are models of stability. They burn with a steady, predictable light, their output changing only over geological timescales. Distant galaxies shine with the combined, averaged-out light of billions of stars, an even more constant glow. But Cygnus X-1 was different. The signal it produced was a chaotic, flickering mess. It did not shine. It sputtered. It flared, dimmed, and surged with a terrifying, unpredictable rhythm. The intensity of its X-ray emission could double in a fraction of a second. Imagine a lighthouse powerful enough to be seen across the galaxy, but instead of a steady beam, its light bulb is crackling and short-circuiting, flashing with the chaotic energy of a lightning storm. This rapid variability was the crucial clue, the key that would unlock the terrifying nature of the object. For something to change its brightness that quickly, it has to be small, incredibly small. Think about it. If a star 1,000,000 miles across suddenly brightens the light from the edge, nearest to you arrives before the light from the far edge. This travel time smears out the signal, smoothing any rapid changes. An object simply cannot change its overall brightness faster than the time it takes light to travel across its own diameter. The flickering of Cygnus X-1 happening on timescales of milliseconds meant that the source of this colossal energy output, this celestial blowtorch, could be no larger than a few hundred miles across. It was a stunning paradox. How could something so small, barely the size of a city, generate more energy in a single second than our own sun does in a day? The scientific community was in an uproar. Every conventional explanation failed. It wasn't a normal star. It was too small and too energetic in the X-ray spectrum. It wasn't a neutron star, the crushed city-sized remnant of a supernova. While incredibly dense, the theories of the time couldn't account for the sheer mass that seemed to be required. It couldn't be a distant galaxy, as the rapid flickering ruled out any large extended object. It was a cosmic conundrum of the highest order, an object with the energy output of a stellar giant crammed into a space smaller than a terrestrial state. It was an engine of impossible efficiency, a concentration of power that defied the known laws of astrophysics. The race was on to find out what it was. The problem was, you can't point a telescope at a set of coordinates that only exist in X-ray data. You need an optical counterpart. You need to find the thing that is screaming. The breakthrough came with the launch of the Uhuru satellite in 1970. Named for the Swahili word for freedom, it was the first dedicated X-ray observatory in orbit. For the first time, astronomers were not limited to 6-minute rocket flights. They had a persistent eye on the high-energy sky. Uhuru could stare at Cygnus X-1, mapping its behavior with unprecedented detail, and most importantly, narrowing its location with far greater precision. Simultaneously, radio astronomers pointed their large dish antennas towards the celestial swan. They found a faint, variable radio source at the same location that Uhuru was pinpointing. The net was closing. With a precise radio position, optical astronomers at the Palomar Observatory could finally bring their powerful telescopes to bear. They began taking long exposure photographs of that tiny patch of sky, a star field crowded with thousands of faint points of light. One of those points was different. Spectroscopic analysis revealed a star catalogued as HDE 226868 that was no ordinary sun. It was a colossal blue supergiant, a stellar titan, some 20 times more massive and hundreds of thousands of times more luminous than our own Sunday, and it was in trouble. The light from this star was performing a strange and telling dance. As astronomers studied its spectrum, they saw the telltale signs of the Doppler effect. Its light was periodically shifted towards the blue and then towards the red. This meant the entire star, a behemoth weighing 20 solar masses, was being thrown around in space. It was orbiting something it was gravitationally bound to, something powerful, and something utterly, completely invisible. The pieces of the puzzle were finally falling into place, but the image they formed was more shocking than anyone had anticipated. Here you had a visible supergiant star, HDE 226868, locked in a tight, frantic orbit with an unseen partner. The orbital period was a mere 5.6 days. For a star that massive to be whipped around so quickly, its companion had to be incredibly massive itself. By applying Kepler's laws of motion, the same principles that govern the planets in our solar system, astronomers could calculate the mass of the invisible object. The number they arrived at was staggering. It had to be at least 10 times the mass of our Sunday, a silent, unseen partner with the gravitational pull of 10 suns all crammed into a space so small that it could flicker in milliseconds. This was the moment of truth, the precipice of a new reality. The checklist of possibilities was run down again, this time with the hard numbers of orbital mechanics. Could it be another star that was simply too dim to see impossible? An object of that mass would be a star itself, and a bright one. Even the faintest main sequence star of 10 solar masses would blaze brightly, easily visible next to its supergiant companion. It wasn't there. Could it be a neutron star? This was the most exotic object astronomers could realistically conceive of at the time, but physics, specifically the work of Oppenheimer and Volkoff, had placed a hard limit on the mass of a neutron star. The incredible pressure of neutron degeneracy, the quantum mechanical rule that prevents neutrons from occupying the same state, could only hold up against gravity to a certain point. That point, the Oppenheimer-Volkoff limit, was thought to be around 3 times the mass of the Sunday Cygnus X-1's invisible companion was far, far heavier. It had crushed that limit. There was only one thing left. One terrifying theoretical possibility that had haunted the pages of physics journals for decades. It was an idea so bizarre, so contrary to common sense, that most physicists, including Einstein himself, considered it a mathematical nightmare, a pathology in the equations of general relativity that couldn't possibly exist in the real universe. A star so massive that when it died and collapsed, nothing could stop it. Not the pressure of electrons, not the pressure of neutrons, nothing. An object that would collapse forever, crushing itself down to an infinitely small point, a singularity. In doing so, it would warp the very fabric of space-time around it so severely that it would literally tear a hole in the universe. It would create a region of space with a gravitational pull so immense that nothing, not even light itself, could escape. A black hole. The evidence was all pointing in one direction. The intense flickering X-rays were not coming from the invisible object itself. They were the death scream of matter being stolen from the visible supergiant star. A river of superheated gas pulled from the star's outer layers by the immense gravity of its companion was swirling into a flattened incandescent disk, an accretion disk, as this matter spiraled inwards, accelerating to near the speed of light. Friction and tidal forces heated it to millions of degrees, causing it to glow with unimaginable intensity in X-rays before taking the final fatal plunge across. The event horizon, the point of no return. The rapid flickering was the chaotic turbulence in this cosmic drain, the last gasp of matter before it vanished from our universe forever. This was the hypothesis, a bold, almost unbelievable explanation for the fury in Cygnus. For the first time, humanity was not just contemplating a black hole as a mathematical curiosity. We were staring at the evidence of its existence. We were witness to a cosmic crime scene with a visible victim being slowly devoured by an invisible assailant. But to claim you have found a monster is an extraordinary thing. To suggest that these ghosts of general relativity were real, tangible objects in our own galactic backyard was a step many were not willing to take. The theory was too new, the implications too profound. It challenged everything we thought we knew about matter, space, and time. It suggested that there were places in the universe where the laws of physics, as we understood them, simply ceased to exist, places from which no information could ever return. The scientific world stood at a crossroads, gazing at a wobbling star in a quiet constellation, and was forced to confront the most profound question it had ever faced. Are we looking at the edge of reality itself? The debate was about to begin, and the universe, as we knew it, would never be the same. What if the most important stories in the universe were being told in a language you couldn't perceive? Imagine a cosmic theatre of unimaginable violence, of stars tearing each other apart, of matter heated to millions of degrees, all playing out just beyond the veil of our senses. For all of human history, this was not imagination. It was our reality. We had been staring at the heavens with one eye shut. Our planet's atmosphere, the very air that gives us life, was also our celestial blindfold, a gossamer veil of gas that dutifully absorbed the most energetic, the most revealing, the most violent dispatches from the cosmos. It was a shield that left us in a state of profound ignorance, letting through the gentle shimmer of starlight while blocking the brutal screams of the universe's high-energy underworld. We lived under a quiet sky, unaware that just overhead a storm of cosmic X-rays was raging, a silent, invisible tempest carrying tales of cosmic cataclysm. Breaking through that barrier, learning to see that hidden light would require more than a new kind of telescope. It would require us to leave our world behind, if only for a few minutes at a time. The story begins not in a pristine observatory on a remote mountaintop, but in the harsh, sun-baked desert of New Mexico, amidst the echoes of global conflict. Here, in the years following the Second World War, the very instruments of destruction were being forged into tools of discovery. Captured German V-2 rockets born from a desire for annihilation were now pointed not at cities but at the heavens. These were the first tentative steps of what would become the space race, a new era of exploration driven by a potent mixture of scientific curiosity and Cold War paranoia. For a small, dedicated group of physicists, these repurposed rockets offered an unprecedented opportunity. They could serve as temporary elevators, lifting scientific instruments above the suffocating blanket of the atmosphere for a few precious, fleeting moments. They were crude, they were unreliable, and they often failed catastrophically, but they were the only way to open a new window on the universe. It was within this high-stakes experimental environment that a young Italian-American physicist named Riccardo Giacconi began to dream. Giacconi, working with a team at a small private company called American Science and Engineering, was a visionary obsessed with a form of light our eyes could never see. He was a pioneer in the nascent field of X-ray astronomy, a discipline that many of his colleagues considered a fool's errand. The logic against it seemed sound. While our own sun emitted a faint trickle of X-rays from its corona, established theories predicted that even the nearest stars would be far too faint in the X-ray spectrum for any conceivable detector to spot. Searching for cosmic X-rays, the consensus went, was like trying to hear a whisper in a hurricane. But Giacconi and his collaborators Bruno Rossi and Herbert Gursky suspected the universe might hold surprises. They understood that X-rays are not the signature of tranquil, stable objects. They are the muzzle flash of cosmic violence. They are forged in environments of extreme temperature and immense gravitational force phenomena, far beyond the placid physics of a typical star. Their initial goal, however, was deceptively modest. They weren't hunting for cosmic monsters. They simply wanted to see if the moon bombarded by solar X-rays might fluoresce glowing faintly in this invisible light, much like a white shirt under a black light. It was a clever, fundable experiment, a plausible first step into the unknown. So it was that on June 18th, 1962, a slender Aerobee, 150-sounding rocket stood poised on its launch pad at the White Sands missile range. Strapped inside its nose cone was Giacconi's precious cargo, a set of 3 Geiger counters designed to capture the telltale signature of high-energy X-ray photons. The plan was simple if terrifyingly fragile. The rocket would scream upwards, punching through the atmosphere for a suborbital flight that would grant its payload a mere 5 minutes and 50 seconds of viewing time above the absorbing layers of air. The entire mission years of work and funding hinged on those 350 seconds. There was no room for error. As the countdown reached 0, the Aerobee ignited, tearing itself from the desert floor on a pillar of fire and smoke. It climbed a tiny needle, stitching a path towards the heavens, carrying humanity's new eyes. Inside the payload, the detectors were programmed to scan the sky, their mechanical gaze sweeping across the constellations as the rocket itself spun slowly for stability. The team on the ground held its breath, tracking the faint radio signal that was their only link to the audacious experiment. The data began to stream back. As they later analyzed the telemetry, a startling picture emerged. The moon, the primary target of their mission, was completely dark. It showed no X-ray fluorescence at all. By that measure, the experiment was a failure. But as they looked at the rest of the data, their frustration turned to sheer astonishment. Their detectors had registered a signal, a massive, overwhelming spike of X-rays, but it wasn't coming from the moon. It was coming from a completely different direction deep in the heart of the Milky Way toward the constellation Scorpius. The signal was 1,000 times stronger than anyone had dared to predict. It was so intense, in fact, that at first they suspected an instrument malfunction, or perhaps even the lingering radiation from a recent high-altitude nuclear test. But the data was clean. The source was real. It was discrete, it was powerful, and it was utterly inexplicable. They had stumbled completely by accident upon the first ever source of X-rays detected from beyond our solar system. They named it Cygnus X-1, a simple, functional designation for what would prove to be a revolutionary discovery. The quiet, peaceful universe they had been taught to believe in was a lie. The cosmos was buzzing with high-energy secrets. Yet Cygnus X-1 wasn't the only ghost in their machine. As they carefully subtracted the signal from this brilliant new source, they noticed something else in the data. The background wasn't entirely smooth. In addition to a faint diffuse glow of X-rays coming from all directions, there seemed to be another, less prominent source of emissions. The detectors, with their wide, imprecise field of view, had swept over it as the rocket tumbled through space. The signal was weaker than that from Cygnus X-1, but it was undeniably present, a secondary pulse in the data stream. Its rough coordinates placed it somewhere in the rich star fields of the Northern Cross within the sprawling constellation of Cygnus the Swan, and so it was given its own plain, unassuming name, Cygnus X-1, the first X-ray source catalogued in that constellation. At that moment it was little more than a curiosity, a secondary anomaly in a mission that had already yielded a spectacular primary discovery. No one on that team could have possibly known that this faint secondary signal was the first whisper of a creature far stranger, far more powerful, and far more consequential than Cygnus X-1. They had unknowingly captured the first light from a true cosmic monster. The discovery of these celestial X-ray beacons threw open the doors to a new kind of astronomy, but it also presented an immediate and deeply frustrating problem: precision. The Geiger counters aboard that first Aerobee rocket were like trying to view the heavens through a frosted bathroom window. They had a field of view that was dozens of degrees wide. Knowing that Cygnus X-1 was somewhere in the constellation, Cygnus was astronomically useless. It was like a detective being told a fugitive was hiding somewhere in New York City. The constellation is a vast celestial landscape filled with millions of stars, nebulae, and clusters. To understand what this object was, they had to find it. They had to pinpoint its location with enough accuracy to bring the world's great optical telescopes to bear to see if this invisible X-ray source corresponded to any visible object. This challenge would consume the better part of a decade, a painstaking campaign of celestial cartography conducted in 5-minute bursts. The solution was a device called a collimator, a simple yet ingenious system of metal slats or tubes placed in front of the detector. A collimator acts like blinders on a horse, restricting the instrument's field of view and allowing it to see only a narrow strip of the sky at any one time. Over the course of the 1,960 seconds, Giacconi's team and other competing groups launched a series of rocket flights, each equipped with more sophisticated collimators, each designed to chip away at the uncertainty surrounding the location of Cygnus X-1. The process was agonizingly slow. Each rocket flight offered another brief, precious glimpse. By placing 2 collimators at an angle to each other, they could create a grid. As the spinning rockets scanned the sky, the source would blink as it passed in and out of the narrow fields of view. By timing these blinks from multiple detectors, they could begin to draw intersecting lines on the map of the sky. With each successful flight, the search area, the error box containing the mysterious object, began to shrink. It was like a slowly focusing image, the blur gradually resolving as the box shrank from the size of an entire constellation down to a patch of sky, small enough to be surveyed by a powerful ground-based telescope. By the late 1,960 seconds, the location had been refined to a tiny patch of sky, but the 5-minute glimpses afforded by sounding rockets were reaching their limit. They were like snapshots of a dynamic churning system offering hints but no continuous story. To truly understand the nature of Cygnus X-1, astronomers needed more than a snapshot. They needed a long, lingering stare. They needed a permanent eye in the sky. That dream became a reality on December 12, 1970, with the launch of a satellite that would forever change high-energy astrophysics. Launched from a platform off the coast of Kenya on that country's Independence Day, it was christened Uhuru, the Swahili word for freedom. It was the first satellite dedicated entirely to X-ray astronomy, a culmination of everything Riccardo Giacconi had been working towards. Unlike the frantic, short-lived rocket flights, Uhuru could orbit the Earth for years, methodically scanning the heavens, its instruments patiently gathering photons, building a comprehensive map of the X-ray universe, and one of its prime targets was the enigmatic source in Cygnus. When Uhuru turned its gaze towards Cygnus X-1, the data that streamed back to Earth was nothing short of shocking. It confirmed that the source was there right where the rocket experiments had predicted, but it revealed something new, something the brief rocket flights could never have captured. The X-ray emission was not steady. It wasn't a constant glow or even a regular pulse like the recently discovered pulsars. Instead, it was a chaotic, violent flickering. The brightness of Cygnus X-1 was changing, wildly doubling or halving its intensity, not over days or hours, or even minutes, but in fractions of a second. It was a celestial strobe light, having a seizure, a frantic cosmic heartbeat that was utterly chaotic. This wild variability, this uncontrolled flickering on timescales as short as a few milliseconds, was the single most important clue yet uncovered, and it presented a profound, mind-bending paradox. In our universe, there is an absolute speed limit, the speed of light. Nothing can travel faster. This simple fact has a critical consequence for astronomers. An object cannot coordinate a change in its brightness like a flicker any faster than the time it takes light to travel from one side of it to the other. Imagine a vast illuminated sphere the size of our sun. For the entire sphere to dim simultaneously, a turn-off signal would have to propagate from some central point to its entire surface. Because that signal can travel no faster than light, it would take several seconds for the whole sun to appear to dim to a distant observer. The object's size therefore places a fundamental limit on how fast it can possibly flicker. A millisecond is 1,000th of a second. For Cygnus X, one to be fluctuating its entire immense energy output on that timescale meant that the source of these X-rays had to be incomprehensibly small. Light can only travel about 300 kilometers or less than 200 miles in a millisecond. The engine driving Cygnus X-1, this powerhouse that was pouring out X-rays with the luminosity of thousands of suns, could be no larger than a small asteroid. Think about that contradiction. The power of a star compressed into a space smaller than a terrestrial city. What kind of object could possibly do that? No known celestial body fit the description. A normal star was millions of kilometers across. A white dwarf, the dense remnant of a dead sun-like star, was the size of the Earth, still far too large. Even a neutron star, the densest form of matter then known, a city-sized corpse of a massive star, had theoretical limits on its stability and behavior that didn't quite match this chaotic, flickering violence. The physics was screaming that something was terribly wrong. Here was an object that broke the known rules of stellar astrophysics. It was impossibly energetic for its impossibly small size. The data from Uhuru had taken a long-standing puzzle and escalated it into a full-blown crisis of cosmology. The mystery of Cygnus X-1 was no longer just about finding an object. It was about confronting an object that, according to the science of the day, should not exist. Armed with Uhuru's precise coordinates and the stunning revelation of its rapid variability, astronomers around the world raced to their optical telescopes. They pointed their colossal mirrors to that exact spot in the sky, the location of this invisible cosmic blowtorch, hoping to finally identify its source. They meticulously photographed the star field, comparing their new images with older photographic plates from decades past, searching for anything unusual, anything out of the ordinary. And what they found was at first a deep disappointment. There was no exploding star, no swirling violent nebula, no peculiar exotic object to be seen. At the heart of the X-ray error box lay nothing more than a perfectly ordinary-looking, if massive, star. It was a blue supergiant, catalogued long before as HDE 226868, a star like countless others scattered across the Milky Way, notable only for its brightness and distance. It was a behemoth, to be sure, some 20 times more massive than our Sun, but it was just a star. And stars, especially stable supergiants like this one, do not emit torrential flickering floods of hard X-rays. They simply can't. So the puzzle deepened into a genuine enigma. The X-rays were real. The chaotic flickering was real. The pinpoint location was now certain. And yet when we looked with our own eyes, all we saw was an innocent bystander, a star that had no business being associated with such celestial violence. The evidence was contradictory, impossible. It was a cosmic crime scene with a confirmed gunshot, a clear trajectory, but the only person in the room was holding a book, not a smoking gun. Could the star be hiding a secret? Or was the source of the X-rays something else entirely? Something lurking right next to the star? Something so strange and so compact that it emitted no visible light of its own. The astronomers had been hunting for a visible counterpart to an invisible light source. They had found one, but it only made the mystery more profound. They were staring at a crime scene with two actors, one brilliantly luminous and placid, the other completely invisible yet furiously violently alive. The stage was now set for a confrontation with an object that lived only in the wilder shores of theory, a gravitational ghost whose existence was about to be dragged screaming into the light. And so the signal from the void continued to scream. That invisible tempest in the constellation Cygnus, a wound in the fabric of space bleeding pure energy, remained a maddening enigma. For years, it was little more than a set of coordinates, a ghost haunting the photographic plates of the world's greatest observatories. Astronomers knew with chilling certainty where the violence was originating. Yet when they aimed their telescopes at that precise point, they found nothing unusual at least. Just a dense, glittering field of stars, a slice of the Milky Way like any other, betraying no hint of the monster that lurked among them. It was a cosmic crime scene with a victim's cry echoing through the universe, but the perpetrator had left no fingerprints, no footprints, no visible trace of its existence. The X-rays were the undeniable proof of a cataclysm, a celestial engine of unimaginable power, yet it was a phantom cloaked in the ordinary darkness between the stars. This profound disconnect between what our new X-ray eyes could see and what our traditional optical telescopes could not presented a paradox that struck at the very heart of astrophysics. Something was profoundly wrong, or perhaps profoundly new. The search for a physical counterpart became an obsession, a new kind of gold rush played out not in the muddy rivers of Earth, but across the photographic archives and observational logs of a global community. The data from the Uhuru satellite had narrowed the search box, but that box was still large enough to contain thousands of distant suns. Which one, if any, was the culprit? Which quiet, unassuming star was secretly accomplice to the fury of Cygnus X-1? The answer would not come from a burst of sudden insight, but from the patient, meticulous work of a detective, one who understood that the most revealing clues are often the most subtle. That detective was a young Canadian astronomer at the University of Toronto's David Dunlap Observatory, Charles Thomas Bolton. In 1971, he possessed the tenacity, the tools, and the crucial intuition to finally put a face to the ghost. He decided to turn his attention to a specific star within the suspect area, a star catalogued as HDE 226868. On paper, it was an unlikely candidate for cosmic mayhem. It wasn't an explosive variable or a dramatic pulsar. It was simply a star. But what a star it was! HDE 226868 is a celestial titan, a blue supergiant of breathtaking scale and power. To even begin to comprehend this star is to recalibrate your entire understanding of the cosmos. If you were to replace our own humble sun with this behemoth, its fiery surface would extend far beyond the orbit of Mercury, scorching the Earth to a cinder. It burns with a ferocity that is difficult to put into words, radiating with the light of over 200,000 suns combined. Its surface temperature is a blistering 30,000 degrees Celsius, a cauldron of elemental fury that gives it a brilliant, almost violent blue-white hue. This is a star living its life in the ultimate fast lane, burning through its nuclear fuel at a profligate rate destined for a spectacular but brief existence. It is a stellar powerhouse, a king among stars, and it sat squarely in the crosshairs of the search for Cygnus X-1. While other astronomers had noted its presence, it was Bolton who decided to interrogate it to force it to give up its secrets. He suspected this magnificent luminous giant was not alone. He suspected it was hiding something in its glare. His method was a masterpiece of astronomical forensics, relying on a principle you experience every single day, the Doppler effect. Think of the siren of a passing ambulance. As it rushes towards you, the sound waves are compressed, raising the pitch. As it speeds away, the waves are stretched, lowering the pitch. This same fundamental principle of physics applies not just to sound, but to light. When a star is moving toward us, its light waves are compressed, shifting them towards the blue end of the spectrum, a blue shift. When it moves away, the light waves are stretched, shifting them to the red end, a red shift. For most stars, this shift is constant, a simple measure of their stately journey through the galaxy. But Bolton was looking for something different. He wasn't interested in a one-way trip. He was looking for a wobble. He was searching for evidence of a dance. Night after night, using the observatory's powerful spectrograph, he performed a delicate dissection of the supergiant's light. A spectrograph acts like a celestial prism, splitting starlight into its constituent colors, revealing a rainbow crossed by dark lines. These lines, called spectral lines, are the chemical fingerprints of the star's atmosphere, unique signatures of elements like hydrogen and helium. If the star was stationary relative to us, these lines would always appear in the same place. But what Bolton found was astonishing. The fingerprints were moving. The spectral lines of HDE 226868 were in constant rhythmic motion. Over a period of days, he watched them systematically shift toward the blue, then swing back and glide toward the red, then return to the blue once more. It was a clear, unambiguous, and repeating pattern. The star was not just traveling through space. It was oscillating. It was lunging toward Earth at incredible speed, then moments later recoiling just as fast. There is only one logical explanation for a star to behave this way. It cannot be wobbling on its own. Some colossal unseen force had to be pulling on it, yanking it back and forth in a gravitational tug-of-war. The blue supergiant, this magnificent celestial monarch, was not the solitary object it appeared to be. It was one half of a binary system locked in a tight, intimate orbit with an invisible partner. The rhythmic shifting of its light was the telltale signature of this cosmic waltz. As HDE 226868 circled its companion, it would at times be moving toward us in its orbit, causing the blue shift. Then as it swung around to the far side of its orbit, it would be moving away from us, causing the red shift. The dance was elegant, precise, and utterly relentless. The period of this celestial ballet was just 5.6 days. Imagine that, a star 30 times more massive than our Sun, completing a full orbit around its partner in less than a week. The speeds involved were mind-boggling, with the supergiant careening through space at hundreds of thousands of kilometers per hour. This was the watershed moment. The X-rays were not coming from the blue supergiant itself. Stars like HDE 226868 are hot, but not nearly hot enough to generate such a ferocious high-energy storm. The X-rays had to be coming from its invisible companion. Bolton had found the lair of the beast. The phantom of Cygnus X-1 now had a home address. It was the dark partner to a star of unimaginable brilliance. The mystery, however, had only deepened, transforming from a question of where to a terrifying question of what. What kind of object could remain completely invisible yet be massive enough to swing a supergiant star around like a dance partner? What kind of cosmic entity could be so gravitationally dominant that it could ensnare a star of this magnitude in such a frantic, high-speed embrace? The discovery of the binary system was not an answer. It was a key unlocking a door to a room far darker and more strange than anyone had dared to imagine. The laws of orbital mechanics, first laid down by Johannes Kepler centuries ago and refined by Isaac Newton, are the bedrock of celestial physics. They are as reliable as the sunrise. They allow us to predict the motions of planets, comets, and stars with breathtaking accuracy. For Bolton and the wider astronomical community, these laws now became a tool, a cosmic scale to weigh the unseen. By carefully measuring the speed of HDE 226868 from its Doppler shift and by timing the 6-day period of its orbit, they could begin to calculate the mass of the object it was orbiting. The logic is inescapable: the faster the visible star is moving, and the tighter its orbit, the more massive its unseen companion must be to hold it captive. A small object could never exert enough gravitational force to whip a supergiant around in such a short time. Whatever was hiding in the dark beside HDE 226868 had to be heavy, incredibly heavy. The initial calculations began to trickle in, first from Bolton's team, then from other groups around the world who rushed to confirm his discovery. And as they did, a sense of profound unease began to spread through the community. The numbers were impossible. The conservative estimates, the most cautious interpretations of the data, suggested that the invisible object in the Cygnus X-1 system had a mass at least 6 times greater than that of our own Sunday. More refined measurements pushed the number higher, 7, 8, then 10 solar masses and even more. The evidence was irrefutable, printed in the plain language of mathematics and light. Yet it flew in the face of everything they thought they knew about the end-of-life options for massive stars. At that time, science recognized only 2 possible fates for a dead star, 2 types of stellar corpses. The first is a white dwarf, the smouldering ember left behind when a star like our Sun runs out of fuel. These objects are incredibly dense, packing the mass of a sun into a sphere the size of the Earth. But there is a strict, well-understood limit to their existence, a cosmic weight limit known as the Chandrasekhar limit. No white dwarf can exist with a mass greater than about 1.4 times that of our Sunday. Any heavier, and its own gravity would overwhelm it, forcing it to collapse further. The companion of HDE 226868, at a minimum of 6 solar masses, was far, far too heavy to be a white dwarf. That possibility was immediately and emphatically ruled out. The second option was a neutron star. These are even more exotic and extreme objects formed in the heart of a supernova, the cataclysmic explosion of a much larger star. A neutron star is one of the densest objects in the known universe, a city-sized sphere of matter so compressed that a single teaspoon of it would weigh billions of tons on Earth. They are the crushed, petrified cores of once mighty suns. But they too have a breaking point. Quantum mechanics dictates a final line of defense against the ultimate crush of gravity. This theoretical maximum mass, known as the Tolman-Oppenheimer-Volkoff limit, was thought to be somewhere between 2 and 3 times the mass of our Sunday. Any stellar core more massive than this, the theory went, would be unable to support itself. The inward pull of its own gravity would become totally unopposed, leading to an unstoppable, catastrophic collapse. And here was the heart of the crisis. The invisible object in Cygnus X-1 weighed at the very least twice the absolute maximum mass of a neutron star. It shattered the limit. It broke the known rules of stellar death. This wasn't just a discovery. It was a contradiction, a scientific paradox of the highest order. The object was there. Its mass was undeniable, written in the gravitational shiver of its companion star. But according to the established physics of the day, it could not exist. The community was faced with a stark, unsettling choice. Either our fundamental understanding of gravity and matter at extreme densities was completely wrong, or there was a third, previously unobserved type of stellar remnant lurking in the cosmos. A third option that theory had predicted, that Einstein's equations had allowed for, but that many astronomers had dismissed as a mathematical fantasy too bizarre to be real. The object was dark, emitting no light of its own. This meant it was not a normal living star. It was a corpse. It was too massive to be a white dwarf. It was far too massive to be a neutron star. Logically, painstakingly, every known possibility had been eliminated. When you have excluded the impossible, Sherlock Holmes famously noted, "Whatever remains, however improbable, must be the truth." And the improbable truth that remained was an object from which nothing, not even light, could escape. A point of infinite density and zero volume, a place where the laws of physics as we know them break down completely. It was a gravitational abyss, a rupture in the very continuum of space-time. Bolton's careful, patient detective work had not just identified a binary star system, it had led humanity to the precipice of the abyss. He had unmasked the phantom of Cygnus, and its true face was that of a monster from our deepest theoretical nightmares. For the first time, we were staring at compelling observational evidence for the existence of a black hole. The realization sent shockwaves through the world of astronomy. This wasn't just an abstract concept on a chalkboard anymore, not just a curious solution to a set of complex equations. This was a real object orbiting a real star in our own galactic backyard. It was a cosmic predator whose defining characteristic was its ability to erase things from the universe. The implications were staggering, forcing a complete rewrite of our stellar bestiary. We had found a new creature in the cosmic zoo, one whose cage was forged from warped space-time and whose appetite was absolute. The mystery of the intense X-rays suddenly began to make a terrifying kind of sense. The invisible monster wasn't just sitting there in the dark, it was feeding, and the brilliant blue supergiant, its beautiful and luminous companion, was its unfortunate, unwitting victim. The crime scene was finally coming into focus, revealing a drama of gravitational theft and cosmic violence on a scale that defied human imagination. The next step was to understand the murder weapon, to decipher how this process of stellar cannibalism could possibly generate a beacon of X-rays so powerful it could be seen from halfway across the galaxy. The ghost had been found. Now we had to witness its gruesome work up close. The star itself, HDE 226868, became our sole witness. This colossal blue supergiant, 30 times more massive than our own sun, was the only thing we could see, the only tangible clue in a mystery that spanned light years. In the previous decades, we had pinpointed the source of those ferocious X-rays to this innocuous-looking point of light, but proving the connection was one thing. Understanding its nature was a challenge of an entirely different magnitude. The star was talking to us, whispering a story of unimaginable violence, but we were only just beginning to learn its language. The key to unlocking its secret was not in the X-rays that screamed from the void, but in the subtle rhythmic motion of the visible star itself. It moved as if tethered to a ghost, a colossal invisible partner swinging it through an unseen gravitational waltz. This was not a gentle sway, but a frantic dance, a star being flung about its orbit at a staggering 200 kilometers per second. To decipher this dance was to weigh the phantom, and so humanity turned its most powerful eyes toward HDE 226868, not to simply take pictures, but to perform a far more delicate kind of cosmic forensics. The tool for this investigation was the spectrograph, a grand instrument that would take the star's ancient light and slice it prism-like into its constituent colors, a brilliant rainbow barcode of its chemical makeup and, most importantly, its motion. Within this spectrum lay fine dark lines, the absorption fingerprints of elements in the star's atmosphere. These lines were the key. They were not fixed. As the star raced towards us in its orbit, its light waves were compressed, squeezed together, shifting the spectral lines ever so slightly towards the blue end of the spectrum. Then, as it swung away, receding into the cosmic dark, its light waves were stretched, pulled apart, shifting the lines inexorably toward the red. This was the Doppler effect, the same principle that alters the pitch of a passing siren now writ large across the heavens. This celestial pulse, a blue shift followed by a red shift repeating, with perfect clockwork precision every 5.6 days, was the star's heartbeat. And by measuring the extremity of that shift, we could measure the speed of its orbit with breathtaking accuracy. Night after night, month after month, astronomers at observatories like Kitt Peak and Mount Palomar trained their telescopes on that single distant star. They captured its light, painstakingly recording the subtle migration of those dark lines. Each data point was a snapshot of a moment in this cosmic ballet, another piece of a puzzle assembled from photons that had traveled for 6,000 years to deliver their message. This was not a quest for a single dramatic discovery, but a slow, meticulous accumulation of evidence, a case being built against the unknown. The process was grueling. It required immense patience, correcting for the Earth's own rotation, and its journey around the Sun, filtering out the noise of our own atmosphere, and isolating that one pure signal from Cygnus. The resulting graph, a graceful sine wave plotting the star's velocity over time, was more than just data. It was a portrait of gravity's dominion. It was the motion of a star held in absolute thrall to something it could not escape, something powerful, compact, and utterly dark. The visible partner was an open book. The true mystery lay with its invisible tormentor. With the orbital period known 5.6 days, and the star's velocity measured, the laws of physics provided a celestial scale. The principles first sketched out by Johannes Kepler in the 17th century and perfected by Isaac Newton were elegant in their simplicity. In any binary system, the orbital speed and period are directly related to the masses of the two objects and the distance between them. Imagine a seesaw in space with the two objects on either end balanced around a common center of mass. By observing how fast one side of the seesaw is moving, you can deduce the weight of the object on the other side. HDE 226868 was one side of the seesaw. Its motion told us everything we needed to know about its unseen companion. The calculations began feeding the observed velocities and orbital period into the unforgiving equations of orbital mechanics. But there was a critical, frustrating complication. A piece of information was missing. We were observing the dance from an unknown angle. This ambiguity, known as the orbital inclination, was a formidable barrier. Were we viewing the Cygnus X-1 system edge-on like looking at a spinning coin from its side? Or were we seeing it more face-on, as if looking down at a spinning vinyl record? This single unknown variable had profound implications. If we were viewing it edge-on, our measured velocity would be the true orbital velocity, and our resulting mass calculation would be accurate. But if the system were tilted at an angle, the blue shifts and red shifts we measured would only represent a fraction of the star's true speed. The star would actually be moving much faster than it appeared, arcing up and down relative to our line of sight in a way we couldn't directly measure. Consequently, the gravitational pull required to sling it around at that true higher speed would have to be far greater, and that in turn meant the unseen companion would have to be far more massive. This inherent uncertainty meant that whatever answer the equations gave us, it would not be a final precise figure. It would be a flaw. It would be a minimum mass, a boundary beneath which the true mass of the cosmic phantom could not possibly fall. The real object could be heavier, perhaps much heavier, but it absolutely could not be lighter. The scientific community held its breath. The numbers were about to deliver a verdict. When the results were finalized, they were staggering. The analysis, pioneered by astronomers like Paul Murdin, Louise Webster, and Tom Bolton, all working independently and converging on the same terrifying conclusion, pointed to an unseen object of at least 6 times the mass of our Sunday. Subsequent, more refined observations would push that number higher, closer to 8, then 10, and eventually beyond. Let that sink in. The minimum possible mass, the most conservative estimate allowed by the data, was 6 solar masses locked into a space so small it emitted no light of its own. This was the turning point. This was the moment the whispers became a roar. Because in the universe, mass is destiny. And for an object of that mass to be invisible, it had to have suffered a fate more extreme than anything we had ever witnessed before. The established physics of stellar evolution offered a clear, unambiguous line in the sand, a point of no return for matter itself. This boundary is known as the Tolman-Oppenheimer-Volkoff limit, or the TOV limit. It is not an arbitrary figure, but a fundamental barrier woven into the fabric of reality. It represents the ultimate battle between two of nature's most powerful forces. When a massive star dies, its core collapses under its own immense gravity. As the collapse accelerates, the crushing force becomes so intense that it smashes protons and electrons together, forming a sea of neutrons. The collapse is then halted almost miraculously by a purely quantum mechanical phenomenon known as neutron degeneracy pressure. This is a repulsive force that prevents neutrons from being squeezed into the same space and state. It is the universe's final desperate attempt to hold back the infinite pull of gravity. A neutron star is the result of this stalemate, an object of unimaginable density, a city-sized atomic nucleus where matter is pushed to its absolute limit. But this defense is not invincible. The physicists Robert Oppenheimer, George Volkoff, and Richard Tolman had calculated the breaking point. They determined that if the collapsing stellar core was more than about 3 times the mass of our Sun, neutron degeneracy pressure would fail, the quantum bulwark would shatter, gravity would win. Nothing, absolutely nothing known to physics could stop the subsequent collapse. The star would simply continue to crush itself down smaller and smaller until it vanished entirely, leaving behind only its disembodied, infinitely powerful gravity. The data from Cygnus X-1 was therefore not just a measurement, it was a judgment. The minimum mass of the unseen companion was at least 6 solar masses, double the absolute maximum allowed for a neutron star. It wasn't just over the limit, it had shattered the limit. It was a physical impossibility for any kind of star, living or dead, to be that massive, that compact, and that dark. A white dwarf was out of the question. They can't exceed 1.4 solar masses. A collection of smaller objects like several neutron stars huddled together was also ruled out. Such a system would be violently unstable and tear itself apart. Could it be a normal dim star we just couldn't see? No. An object of 6 or more solar masses, even a faint one, would be a star of considerable luminosity. We would have detected its light, its heat, its presence in the spectrum of its brighter companion. But there was nothing, only emptiness, only the X-rays. Only the terrifying gravitational grip on HDE 226868. By a process of pure logical elimination, astronomers were being backed into a corner, forced to confront a conclusion that many still found philosophically and intuitively repellent. The dark companion of Cygnus X-1 could only be one thing. It had to be a black hole, the first of its kind ever to be found. This dawning realization sent shockwaves through the world of physics, crystallizing a debate that had been simmering for decades. The intellectual struggle was perfectly encapsulated in a famous good-natured wager made in 1974. On one side was Kip Thorne, a brilliant Caltech physicist, and one of the world's leading experts on Einstein's general theory of relativity. Thorne, a true believer in Einstein's most exotic predictions, was utterly convinced by the mounting evidence. He felt the orbital data was definitive. He bet that Cygnus X-1 was without a doubt a black hole. On the other side was perhaps the most famous scientist in the world, Stephen Hawking. Hawking, despite his own groundbreaking theoretical work on black holes, was a profound skeptic. His reluctance was not born of ignorance but of a deep unease with one of the central implications of black holes, the information loss paradox. General relativity suggested that anything falling into a black hole was lost forever, its information erased from the universe. This violated the fundamental tenets of quantum mechanics, and Hawking found the idea abhorrent. He famously quipped, "God not only plays dice, but sometimes he throws them where they cannot be seen." He couldn't accept that the universe could be so fundamentally untidy. So driven by this deep physical intuition, he bet against Thorne. He wagered that Cygnus X-1 was not a black hole. The stakes of the bet were not monetary but playfully intellectual. If Hawking won, Thorne would have to buy him a 4-year subscription to the satirical magazine Time's Private Eye asterisk. If Thorne won, Hawking would have to purchase for him a 1-year subscription to Time's Penthouse Times magazine, a choice made, as Thorne later explained, to annoy Hawking's more puritanical colleagues. This bet was far more than a simple office pool. It was the public face of a monumental paradigm shift. It represented the scientific community grappling with its own discoveries, the tension between the cold, hard data from the heavens and the deeply ingrained theoretical principles that seemed to be bending under the weight of this new reality. For years the bet stood. More data poured in. X-ray observatories in space refined their measurements of the flickering radiation from the accretion disk, the swirling vortex of superheated gas being stripped from HDE 226868 and spiraling to its doom. The rapid millisecond variations in X-ray brightness confirmed that the source had to be extraordinarily small, no larger than a few hundred kilometers across. The mass estimates became more and more robust, climbing higher and higher above the Tolman-Oppenheimer-Volkoff limit. The case became overwhelming, the evidence irrefutable. The ghost in the machine was slowly acquiring a solid, terrifying form. Every alternative explanation had been tested and had crumbled under scrutiny. Every new observation only strengthened the case for the impossible. The universe, it seemed, was indeed home to these gravitational ghosts. In 1990, after 16 years of holding out, the evidence became too much for even a mind as formidable as Stephen Hawking's. With characteristic humor and grace, he admitted defeat. He conceded the bet. In a famous gesture, he broke into Kip Thorne's office while Thorne was away in Russia and officially signed the original written wager, conceding that Cygnus X-1 was in fact a black hole. He later lamented with a twinkle in his eye that he had lost the bet, even though his theoretical objections about information loss remained a puzzle that physicists are still struggling with to this day. True to his word, he provided Thorne with the magazine subscription a humorous footnote at the end of one of the 20th century's greatest scientific detective stories. Hawking's concession was more than just the settling of a friendly rivalry. It was a symbolic moment of surrender for the entire scientific establishment. It was the final definitive acknowledgement that these objects, once the stuff of pure mathematical fancy, were real physical entities scattered throughout our cosmos. The discovery of Cygnus X-1, confirmed by the patient study of a wobbling star, had transformed black holes from a theoretical curiosity into an observational reality. We had not merely found a new type of object, we had opened a door into a new realm of physics, a place where space and time become warped and broken, where the rules of our familiar world no longer apply. The phantom in Cygnus was the first specimen, our first chance to study the edge of infinity. The invisible monster now had a weight, a location, and a name, and with its confirmation, the true age of black hole astronomy had at long last truly begun. The focus would now shift from asking times if times they exist, to a far more profound and exhilarating question: what happens there? The number was on the page, a stark calculation that defied belief. A shadow companion, a gravitational ghost weighing more than 10 of our suns. For many astronomers, it was an intellectual bridge too far. Science demands more than a single shocking inference. It demands a body of evidence. It requires that every other possibility, no matter how remote, be hunted down and eliminated. A ghost in the machine of the cosmos could not be accepted on faith. It had to be proven, and the proof, it turned out, was hidden in the very light that first betrayed its existence. The X-rays streaming from Cygnus X-1 were more than just a beacon. They were a message, a frantic, shimmering language written in high-energy photons. And to decipher that language, we had to look closer at the crime scene itself, at the magnificent, doomed supergiant HDE 226868. Imagine you are standing on the surface of this colossal blue star. It is a world of unimaginable scale and violence, a sphere of incandescent gas 30 times wider than our own Sunday. Its stellar winds howl into space, shedding mass at a furious rate. But close by, far too close, lurks its invisible partner, the dark enigma. Its gravitational presence is not gentle, it is a constant predatory pull. Like any star, HDE 226868 exists in a delicate balance, its own gravity pulling it inward while the fusion in its core pushes it out. But the proximity of its massive companion warps this reality. Space itself is distorted here, creating a gravitational boundary, a teardrop-shaped zone of influence around the star known as the Roche lobe. It is a cosmic line in the sand, an invisible point of no return. For eons, the supergiant lived within this gravitational safe zone. But stars like this are not static. As they age, they swell, their outer layers expanding like a slow-motion explosion. Inevitably, inexorably, the outer atmosphere of HDE 226868 began to stretch to distend until it breached the Roche lobe. The moment it crossed that threshold, the rules changed. The gas in its outermost layers no longer belonged to the star. It was captured, ensnared by a gravitational pull it could not escape. A river of stolen star stuff began to flow from the visible giant towards the unseen object, a silent, luminous hemorrhage across the void. This was not a gentle siphoning. It was an act of cosmic piracy on a scale that beggars the imagination. A stream of plasma hotter than any furnace on Earth was being pulled away from its parent star, embarking on a final one-way journey. But this stolen material does not simply fall straight in. Just as a planet orbits a star, this gas carries with it the momentum of its former life, a colossal angular momentum from the supergiant's own rotation. Think of water circling a drain. It doesn't drop directly down the hole. It is forced into a spiral, a vortex that accelerates as it approaches the center. The same principle, one of the most fundamental in physics, governs this river of plasma. Forced into a spiraling path, the gas cannot escape its fate, but it can delay it. It flattens out, smeared by tidal forces, and its own orbital velocity, forming one of the most extraordinary and violent structures in the universe, an accretion disk. This is not a solid object like the rings of Saturn. It is a cosmic grinding wheel, a swirling maelstrom of superheated gas, a vortex of incandescent plasma stretching for millions of kilometers. The inner edge of this disk spins at truly staggering speeds, approaching a significant fraction of the speed of light. Here in this cosmic mosh pit, the laws of physics are pushed to their absolute limits. Trillions of tons of gas particles, all moving in the same general direction but at slightly different speeds, jostle and collide. The result is friction, but on a scale so immense it becomes the most efficient engine of destruction in the cosmos. This is not the gentle warmth of a campfire. This is friction that heats the gas to temperatures of millions, even tens of millions of degrees Celsius, far hotter than the core of the Sunday. At these temperatures, matter cannot remain a simple gas. Atoms are stripped bare of their electrons, creating a turbulent sea of plasma that glows not with visible light but with a torrent of high-energy X-rays. The accretion disk becomes a celestial blowtorch, a source of radiation so powerful it can outshine entire galaxies. The X-rays that the Uhuru satellite first detected, the very signals that put Cygnus X-1 on the map, were not coming from the invisible object itself. They were the death cry of matter, a final incandescent farewell from the edge of the abyss. This understanding was a monumental leap forward. It provided a physical mechanism, a plausible story for where the X-rays came from. The theory beautifully explained how a non-luminous object could be responsible for one of the brightest X-ray sources in the sky. The grand theft of stellar material and its subsequent superheating in a swirling disk of doom was a compelling narrative. It fit the observations, it satisfied the physics. Yet for the most rigorous skeptics, it still wasn't enough. A particularly exotic type of neutron star, they argued, or a complex triple star system, might be able to mimic such a scenario. The case for the black hole was strong, but it was not yet incontrovertible. The final definitive piece of evidence, the smoking gun that would silence the doubters, was still hiding in the data. It wasn't in the brightness of the X-rays or their energy. It was in their timing. It was in their rhythm. When astronomers looked at the X-ray signal from Cygnus X-1 with ever more sensitive instruments, they saw something deeply strange. The light was not steady. It wasn't a smooth, constant stream. Instead, it flickered. It was a wild, chaotic, unpredictable strobe effect, with the brightness changing dramatically from one moment to the next. This wasn't a gentle pulse or a regular beat. It was a cosmic cacophony. The intensity of the X-rays could double or halve in less than a tenth of a second. Sometimes, the changes were even faster, occurring on timescales of just a few milliseconds. This rapid, irregular flickering was the key. It was the secret language of the object, the one that could finally reveal its true nature. To understand why, you have to grasp one of the universe's most fundamental speed limits, a rule that nothing can break: the speed of light. Imagine you have a vast glowing object, perhaps the size of a normal star, and you want to make it flicker. You want its entire surface to brighten and dim in perfect unison. You can't. If a flare erupts on one side of the star, the light from that event travels outward at the speed of light. For the other side of the star to know about the flare and react to that information must cross the entire diameter of the star. This takes time. For a star the size of our Sun, it would take several seconds. This inherent delay smears out any rapid changes. A large object simply cannot coordinate a rapid flicker across its entire surface. It's like trying to get a stadium of 1 million people to all flip a card at the exact same instant. No matter how good the signal, there will be a slight delay, a wave of action that blurs the overall effect. A fast flicker, therefore, is an unmistakable signature of a small source. The speed of the flicker places a hard, absolute limit on the size of the region producing the light. This was the calculation that changed everything. The flickering from Cygnus X-1 was observed on timescales as short as 1/1000th of a second. In 1 millisecond, light can only travel about 300 kilometers or less than 200 miles. This meant that the powerhouse region of the accretion disk, the inferno generating this torrent of X-rays, could be no larger than a few hundred kilometers across. Let that sink in. All the energy, all the fury, all the light was erupting from a zone smaller than the state of Ohio. And this tiny region contained an object that orbital mechanics had already told us was more than 10 times the mass of the Sunday. The pieces of the puzzle were now locking into place, and the picture they formed was terrifying and awe-inspiring. The universe was presenting us with an object that had the mass of a giant star but was crammed into a space smaller than a city on Earth. This single fact, this irrefutable conclusion drawn from the speed of light, acted as a wrecking ball to every alternative theory. Could it be a strange, supermassive neutron star? Absolutely not. The laws of nuclear physics are clear on this. There is a theoretical maximum mass for a neutron star, the Tolman-Oppenheimer-Volkoff limit, beyond which its own gravity will crush it out of existence. That limit is thought to be around 2, maybe 3 solar masses at the absolute extreme. Cygnus X-1 was at least 3 times heavier than the most massive neutron star that could possibly exist. Furthermore, the rapid X-ray bursts from many neutron stars are often associated with their powerful magnetic fields and rapid clockwork rotation, producing a regular pulse. The signal from Cygnus X-1 was pure, unadulterated chaos, the signature of turbulence, not rotation. The neutron star hypothesis was dead. What about a more complex, unseen system? Perhaps a triple star system where 2 compact objects were orbiting each other, somehow creating the illusion of a single massive one. This idea too crumbled under the weight of the flickering. Such a system would be vastly larger than the 300-kilometer region demanded by the light variations. Any X-rays produced would come from a broad, smeared-out area incapable of the near-instantaneous changes being observed. The flickering acted as a cosmic ruler, and it measured a space far too small to contain multiple stars. Every alternative explanation that scientists could devise was systematically dismantled by this one simple observation. The combination of immense mass and minuscule size left only one candidate standing, one object that theory had predicted but no one had ever seen. An object with a gravitational field so intense that it collapsed in on itself, crushing matter down to an infinitesimal point of infinite density, a singularity. The rapid, chaotic flickering was more than just proof of a compact object. It was the very signature of matter's final violent moments before annihilation. What we were seeing was not the steady glow from a solid surface, but the turbulent last gasp of gas at the inner edge of the accretion disk. We were witnessing clumps of plasma torn from a star spiraling into oblivion at nearly the speed of light. Each flicker was another blob of matter taking the final plunge, releasing a brilliant flash of energy as it crossed the threshold from which nothing, not even light, can escape. We were watching the ragged, sputtering flame of a candle at the edge of the event horizon. The black hole itself is by definition dark, but its immediate environment, the zone where space-time itself is dragged into a terminal vortex, is the most luminous and violent place in the cosmos. The evidence was no longer merely circumstantial, it was direct, it was profound. The ghost in Cygnus was no longer a phantom, inferred from gravitational wobbles. It now had a fingerprint, a chaotic high-energy signature that screamed its identity across 6,000 light-years of space. The scientific community, a body built on skepticism and rigorous proof, began to reach a consensus. The arguments against the black hole had fallen one by one, defeated by the relentless accumulation of data. The orbital motion had revealed its mass. The physics of accretion had explained its light, and the flickering of that light had revealed its impossible nature. Cygnus X-1 was not a star, it was a gravitational abyss. The case was closing not just on a local cosmic mystery, but on one of the deepest questions about the nature of reality itself. Einstein's most extreme prediction, a place where his own equations broke down, was not just a mathematical curiosity. It was real, and one was right here in our own galactic backyard. But this discovery would prove to be more than just the solution to a single puzzle. It was a key unlocking a door to a new and violent cosmos, forcing us to confront the most extreme physics and the ultimate fate of stars. For if one existed, there must be others. The hunt had just begun. The case against Cygnus X-1 was compelling a prosecutor's dream. It possessed the motive of immense gravity, a partner star as its witness, and a chaotic, flickering alibi that only pointed toward a compact, violent nature. For years, the evidence had mounted each new observation, adding another layer of suspicion. The sheer mass, calculated from the sorrowful waltz of its companion, had already pushed the object far beyond the theoretical limits of a neutron star. No known form of matter, no conceivable stellar corpse could support itself against its own crushing weight if it were more than 3 times the mass of our Sun. Cygnus X-1 at more than 15 solar masses had flagrantly violated that sacred limit. Yet in the grand celestial court of scientific opinion, a verdict remained elusive. There was still room for doubt, for a sliver of the unknown. Perhaps there existed some exotic state of matter, some new physics that we hadn't yet dreamed of that could masquerade as a black hole. The evidence was powerful, yes, but it was circumstantial. It described the time's effects, times of a monster, but no one had seen the monster itself. To truly convict Cygnus X-1 to close the case for good, we needed more than just a measurement of its weight or the frantic pattern of its light. We needed a fingerprint taken from the very edge of the abyss. We needed to catch the laws of physics themselves being twisted into new, unrecognizable shapes, a direct confession extracted from the fabric of space-time. The tools of the past, sensitive as they were, could only listen to the distant shouting. To hear the whisper from the event horizon, we would need a new kind of ear, an instrument capable of dissecting light with a precision previously unimaginable. That new era dawned not with a single telescope, but with a flotilla. Orbiting high above the blurring veil of Earth's atmosphere, observatories like Japan's ASCA, Europe's XMM Newton, and NASA's Chandra X-ray Observatory turned their golden eyes toward the heavens. These were not mere telescopes, they were cosmic spectrometers of exquisite power. They could do more than just count X-ray photons. They could measure the precise energy of each one, transforming the chaotic blaze of Cygnus X-1 into a detailed spectrum, a rainbow of high-energy light that held the deepest secrets of its origin. For decades, we had been staring at the inferno of the accretion disk, the swirling vortex of stolen gas from HDE 226868, heated to millions of degrees. Now, for the first time, we had the ability to probe its innermost sanctum, the final desperate orbit where matter screams its last before surrendering to eternity. And it was here in this maelstrom of unimaginable violence that astronomers knew to look for a very specific, very telling clue. It was a signal from one of the most common elements in the universe, iron. Under normal conditions, an atom of iron, when bombarded with X-rays, emits a fluorescent glow at a very particular, very reliable energy. It sings a single pure note at precisely 6.4 keV. This is its spectral line, an atomic fingerprint as unique and as constant as the speed of light itself. Across the universe, from the core of our own planet to the most distant galaxies, iron always sings this same song. Scientists expected to see this sharp, narrow spike of iron emission rising above the general chaos of the accretion disk's glow. It would be the baseline, the control group, the one predictable feature in a system defined by its unpredictability. It would be the steady rhythm against which the wild jazz could be measured. So the new generation of observatories stared, accumulating photons hour after hour, building a portrait of Cygnus X, one with a clarity that was once science fiction. The data streamed back to Earth to be processed, analyzed, and finally revealed. And when the spectrum was finally plotted, there was a collective intake of breath in control rooms and university offices around the world. The iron line was there, but it was not the line anyone expected. It wasn't a sharp, narrow spike. It was not a pure single note. What they saw instead was a grotesque distortion, a spectral scream. The peak was still visible, but it was smeared and misshapen like a familiar face seen through a warped and twisted lens. It rose not as a clean pinnacle, but as a broad asymmetrical hill with a long extended tail stretching down into the lower energies. This was it. This was the confession written in the language of light and gravity. This strange, distorted shape was not a flaw in the instruments. It was the signature of Albert Einstein's relativity pushed to its absolute limit. It was the gravitational fingerprint of a black hole. Each part of that warped profile told a story, a chapter in the final moments of matter. The broadness of the peak was the first clue. In the accretion disk, gas isn't falling straight in. It's orbiting, whirling around the central object at breathtaking speeds, a significant fraction of the speed of light. This incredible velocity triggers an effect you've experienced yourself, the Doppler shift. Just as the siren of an ambulance changes pitch as it rushes past you, the light from the orbiting iron atoms is also shifted in energy. The iron on the side of the disk spinning towards us would have its light blue shifted, its energy boosted and crammed into a higher frequency. The iron on the side spinning away would be red shifted, its light stretched and weakened. Combined, these two effects would take the single sharp line of stationary iron and smear it out into a broad profile, a clear indicator of rapid rotation. This by itself was astounding. It painted a picture of a cosmic whirlpool spinning at speeds that defied conventional imagination. But it was the shape times of the line, its profound asymmetry that sealed the case. The profile was not a symmetrical bell curve. It was skewed with a dramatically extended wing on the low energy or red side. This was not something classical physics could explain. This was the ghost in the machine. It was the calling card of extreme gravity. This skewed tail was the result of one of the most bizarre and powerful predictions of general relativity gravitational redshift. Einstein taught us that gravity is the curvature of space-time. A massive object like a black hole creates a deep well in that fabric. Light as it travels must obey the contours of this warped reality. A photon of light emitted from deep within that gravitational well near the edge of the event horizon must climb its way out to reach our telescopes. But this climb is not free. The black hole's gravity exacts a toll. It literally stretches the photon, stealing its energy, shifting it to a lower, redder frequency. The closer to the event horizon an atom of iron emits its light, the more energy that light loses on its journey out of the gravity well. That long red tail on the iron line profile was a direct map of this effect. It was the spectral echo of photons that had fought and barely escaped the gravitational pull of an unseen monster. They were wounded messengers arriving at our detectors, weakened and stretched, carrying an unambiguous story of the titanic struggle they had just endured. For the first time, we were not just inferring the black hole's presence, we were directly measuring its distortion of space-time itself. We could see the shadow it cast upon the very light that bathed it. By analysing the precise shape of this relativistically broadened iron line, astronomers could now do something that once seemed impossible. They could measure the inner boundary of the accretion disk. They could calculate just how close matter could orbit before it was lost forever. The data revealed an inner edge so close to the compact object that no neutron star, no matter how dense, could possibly allow it. The matter was orbiting in a region where gravity was so intense, where space-time was so violently curved that only an event horizon could be waiting below. The gas was swirling not around a hard surface, but around a point of no return. This was the smoking gun. In fact, it was more than that. It was the bullet, the ballistics report, and a videotaped confession all in one. The circumstantial case was now closed, replaced by undeniable physical proof. Let us stand back and admire the sheer weight of the evidence, the beautiful, unwavering coherence of the story it told. First, we had the mass. From the gentle, predictable orbit of a living star, HDE 226868, we deduced the presence of a dark companion of impossible weight, a gravitational anchor far too heavy to be a star of any conventional kind. Second, we had the variability. The X-ray light from Cygnus X-1 didn't just shine, it flickered and stormed on timescales of milliseconds. This rapid-fire messaging screamed that the engine powering this lighthouse had to be incredibly small, confined to a region no larger than a city. A massive object, yet also an impossibly compact one. And now third, we had the final damning piece of testimony. The spectral signature of iron atoms tortured and distorted by physics that can only exist in the immediate vicinity of an event horizon. We saw their light Doppler shifted by orbital speeds approaching the ultimate cosmic limit. We saw their light gravitationally redshifted by a gravity well so deep it was literally stealing energy from the light itself. Every single piece of evidence, gathered over decades by different teams using different methods and different technologies, pointed to the exact same inescapable conclusion. There was no more room for exotic alternatives. There was no more appeal to unknown physics. The puzzle was solved. The verdict was in. The international scientific community, a body famously skeptical and difficult to unite, reached a near-universal consensus. The debate that had raged for a generation, that had pitted brilliant minds against each other, that had inspired wagers and fueled discovery, was finally over. Cygnus X-1, the enigmatic source of X-rays in the constellation of the Swan, was without any reasonable doubt a black hole. It was real. The mathematical abstraction that had leaked from Einstein's equations, the theoretical monster that had haunted the nightmares of physicists, had finally been found, catalogued, and observed. It was a moment of profound triumph for human curiosity, a testament to our relentless refusal to accept a mystery without trying to solve it. Stephen Hawking, who had famously wagered a magazine subscription against Kip Thorne that Cygnus X-1 was times not times a black hole, finally conceded defeat. In a characteristically graceful and humorous gesture, he admitted he was wrong, lamenting that his work on black hole thermodynamics would have been for nothing if these objects didn't actually exist in nature. The discovery transformed black holes overnight. They migrated from the chalkboards of theorists to the observation logs of astronomers. They were no longer just fascinating what-ifs. They were now a fundamental component of the cosmos' celestial objects to be studied, classified, and understood. Cygnus X-1 became the prototype, the Rosetta Stone for a whole new class of cosmic beasts. Its confirmation didn't just solve a local mystery, it unlocked a new chapter in our understanding of the universe's most extreme phenomena. It gave us the confidence to hunt for others, to recognize their telltale signs elsewhere. And once we truly knew what to look for, we began to see them everywhere. The universe, it turned out, was teeming with these dark hearts of gravity, but this first one, this pioneer, would always hold a special place. It was the object that forced us to accept one of the most unsettling truths in all of science, that there are places in our universe where the rules as we know them break down, where matter can be crushed out of existence, and from which not even light can escape. We had proven the monster was real. Now we had to understand its role in the grand cosmic ecosystem. For the discovery of Cygnus X-1 was not an ending. It was the beginning of a far deeper and more complex journey into the dark. And so the whisper in the static, the ghost haunting the constellation of the Swan, was finally given a name. No longer a phantom, no longer a mere theoretical curiosity, it became a place on the cosmic map, Cygnus X-1. With its confirmation, a conceptual dam that had held for decades finally broke, unleashing a torrent of new understanding that would reshape the very landscape of astrophysics. You see, the universe we inhabited before this discovery was in a profound sense tamer. It was a cosmos of stars and planets, of nebulae and galaxies, all obeying laws that, while complex, felt graspable, almost comfortable. The idea of a true singularity, a point of infinite density where the rules of physics simply ceased to function, was a monster lurking in the mathematical shadows, a convenient fiction for theorists, but not a physical reality you could point a telescope at. Cygnus X-1 dragged that monster into the light. It transformed the abstract into the observable, the mathematical into the material. It told us in no uncertain terms that the universe was wilder, more violent, and infinitely more strange than we had ever dared to imagine. The discovery wasn't just another celestial object catalogued, it was a fundamental shift in our cosmic worldview, as significant as the realization that the Earth was not the center of everything. It was the moment humanity confirmed that the fabric of space-time itself could be torn, that gravity could become so powerful it could imprison light, that matter could be crushed out of existence. This single invisible object, 9,000 light-years away, became the definitive proof that the universe contained points of no return. It was the first true abyss we had ever found. Before its unmasking, Albert Einstein's theory of general relativity, while spectacularly successful in predicting the bending of starlight and the orbits of planets, had never been tested in its most extreme manifestation. The black hole was its ultimate, most terrifying prediction, a solution to his elegant equations that even he found difficult to accept. It was a prediction of such radical strangeness that it seemed to belong more to metaphysics than to physics. Cygnus X-1 changed everything. It ceased to be an equation on a chalkboard and became a veritable laboratory for gravity at its most severe. Here, in the maelstrom of its accretion disk, we could finally witness Einstein's universe in its rawest form. The light from HDE 226868 its captured companion star doesn't just fall into the black hole, it journeys through a space-time landscape so warped that our terrestrial intuition completely fails us. As that stolen gas spirals inward, it is accelerated to nearly the speed of light, heated to millions of degrees, creating the very X-ray blaze that first gave the object away. But within that blaze are the subtle signatures of relativity in action. We can see the evidence of gravitational redshift, where light climbing out of that impossibly deep gravity well is stretched, its energy sapped, its wavelength shifted towards the red end of the spectrum. It is a direct measurement of light itself, struggling to escape gravity's clutches, a perfect confirmation of Einstein's predictions. Furthermore, the dizzying spin of Cygnus X-1, a remnant of the collapsing star's angular momentum, literally drags the fabric of space-time around with it. This phenomenon, known as frame dragging or the lens-tharing effect, is a breathtaking concept. It means that near the black hole space itself is a swirling vortex. Imagine a spinning ball submerged in honey. The honey closest to the ball is dragged around by its motion. Now replace the ball with a city-sized object of unimaginable density and the honey with the four-dimensional universe. That is the reality around Cygnus X-1. We have observed the effects of this cosmic gyroscope in the flickering and warping of the accretion disk, seeing matter wobbling not because of its own motion, but because the very space it occupies is being violently twisted. This was no longer a theoretical footnote, it was a measurable, observable reality. Cygnus X-1 became the ultimate proving ground, the celestial crucible where the most bizarre implications of general relativity were forged into hard observational fact. It validated a century of theoretical work in the most spectacular fashion imaginable, demonstrating that the universe is indeed governed by this beautiful yet terrifying geometric dance of mass, energy, and space-time. The legacy of Cygnus X-1 extends far beyond the realm of gravity. It reached back in time, forcing us to completely rewrite the final act in the lives of the most massive stars. For generations, we understood that stars died, but their deaths left behind remnants we could comprehend, the glowing embers of white dwarfs or the hyperdense spinning cores of neutron stars. There was a belief, an implicit assumption, that there was always times something, times left, a tangible corpse that still played by the known rules of matter. The existence of a black hole at the heart of the Cygnus system shattered that comforting notion. It presented us with the evidence for a third, far more dramatic stellar fate. It taught us that for stars born with truly enormous mass, far exceeding that of our own sun, there is a point of no return built into their very nature. When such a star exhausts its nuclear fuel, the outward pressure that has supported it for millions of years vanishes in an instant. Gravity, the force it had battled its entire life, finally wins a total and catastrophic victory. The star's core collapses under its own immense weight, and if that core is massive enough, roughly more than 3 times the mass of our Sun, there is nothing in the known universe that can halt the collapse. Not the pressure of electrons which holds up a white dwarf. Not even the formidable strength of neutrons packed shoulder to shoulder, which defines a neutron star. The collapse becomes unstoppable, absolute. The core implodes past the neutron star limit, crushing itself smaller and smaller, the density skyrocketing towards infinity. It is a process of cosmic annihilation where a magnificent giant star is squeezed into a point of zero volume, leaving behind only its gravitational ghost. Cygnus X-1 was the first empirical proof of this terrifying process. By carefully measuring the orbit of its companion star HDE 226868, we could weigh the unseen object. The result was unequivocal. Its mass, estimated today to be around 21 times that of our Sun, was far too great for it to be a white dwarf or a neutron star. There was simply no other known object that could pack so much mass into such a small dark volume. It had times to be a black hole. This discovery provided the critical data point that anchored our models of stellar evolution. It gave us the observational evidence to define the mass thresholds that dictate a star's ultimate destiny. We could now look at a young massive star forming in a nebula and predict with chilling certainty that its ultimate fate was to vanish from the visible universe, leaving behind nothing but a rupture in space-time. Every subsequent discovery of a stellar mass black hole has built upon the foundation laid by Cygnus X-1, refining our understanding of supernovae, hypernovae, and the complex alchemy that occurs in the final violent moments of a star's life. It transformed the death of a star from a simple endpoint into a gateway to a new and profoundly mysterious state of existence. Perhaps its most practical and far-reaching legacy is that Cygnus X-1 became our Rosetta Stone. It provided the archetypal blueprint, the quintessential field guide for how to hunt for these invisible monsters across the cosmos. Before its discovery, the search for black holes was a purely theoretical exercise, a hunt for an object that by its very nature could not be seen. How do you find something that emits no light? Cygnus X-1 gave us the answer. You don't look for the black hole itself, you look for the chaos it creates. You look for its gravitational fingerprint left on the surrounding universe. The method pioneered in the Swan constellation became the standard operating procedure. First, you search the skies for powerful, erratic sources of X-rays. This high-energy radiation is the telltale scream of matter being superheated and torn apart as it's pulled into a deep gravitational well. It is the signature of a cosmic feeding frenzy. Once you find such a source, the next step is to look for a visible star at the same location, a normal star that appears to be orbiting nothing. You then use the Doppler effect, analyzing the light from that visible star. As it moves towards us in its orbit, its light is compressed, shifted towards the blue. As it moves away, its light is stretched, shifted towards the red. This rhythmic shift in color allows you to precisely measure the star's orbital speed and period. With these two pieces of information, using the same laws of gravity that Kepler used to understand our solar system, you can calculate the mass of the unseen companion it is dancing with. This is the final crucial test. If the mass of that invisible object is greater than the absolute upper limit for a neutron star, you have found your quarry. You have bagged a black hole. This exact methodology, find the X-rays, watch the wobbly star, weigh the invisible partner, has been used to uncover the dozens of stellar mass black holes we now know of within our own Milky Way galaxy. Systems like V404 Cygni, with its own spectacular outbursts, or GROJ 1000, 655-40, which blasts out relativistic jets of plasma, were all found by following the trail blazed by Cygnus X-1. It gave us the playbook, transforming black hole hunting from a speculative quest into a systematic observational science. Every time a new black hole candidate is announced, its confirmation rests upon the same fundamental principles of evidence first established in the study of that one enigmatic system. It democratized the search, allowing astronomers around the world to join the hunt for the universe's most elusive inhabitants. Without the template provided by Cygnus X-1, our catalogue of known black holes would be vastly smaller, and our understanding of their population and influence throughout the galaxy would remain shrouded in speculation. It gave us the eyes to see the invisible. Even now, more than half a century after its discovery, first sent shockwaves through the scientific community, Cygnus X-1 is not a closed chapter. It is not a historical artifact to be admired from a distance. It remains an active, vibrant, and essential cosmic laboratory, a celestial gift that keeps on giving. With each new generation of telescopes, both on the ground and in space, we are able to probe this system with ever-increasing precision, peeling back new layers of its profound mystery. The Chandra X-ray Observatory, NASA's flagship X-ray telescope, has stared at Cygnus X-1 for countless hours, mapping the flow of its accretion disk with breathtaking detail. It has allowed us to study the rapid flickering, the quasi-periodic oscillations in the X-ray signal, which we now understand are linked to reverberations and instabilities in the innermost regions of the disk just moments before matter takes its final plunge across the event horizon. These flickers are echoes from the very edge of oblivion, giving us crucial information about the structure of space-time in the strong field limit. Observations from the Hubble Space Telescope, working in visible and ultraviolet light, continue to monitor the beleaguered companion star HDE 226868, studying the powerful stellar winds that pour from its surface and feed the black hole. By understanding the donor star, we better understand the fuel supply that powers the entire system. Radio telescopes, meanwhile, have given us our best views of the powerful relativistic jets that are being launched from the black hole's poles. These jets are colossal particle accelerators flinging matter out into interstellar space at nearly the speed of light. Yet the exact mechanism by which a black hole, an object famous for pulling things in, can become one of the universe's most efficient engines for blasting things out, remains one of the greatest unsolved puzzles in astrophysics. Cygnus X-1 being so relatively close and bright offers us our best chance to solve it. It is our premier testing ground for models of jet formation, allowing us to see how the launching of these jets is tied to the state and flow of the accretion disk. The questions we ask of it today are deeper and more fundamental than ever before. Can we use subtle observations of its orbit to find definitive proof of Hawking radiation, the faint glow that black holes are predicted to emit? Can we use its light echoes to map the geometry of space-time right down to the event horizon, the surface of no return? Could it hold the key to understanding the information paradox? The profound conflict between general relativity and quantum mechanics that asks what happens to the information of the matter that falls into a black hole. These are the frontier questions of 21st century physics, and Cygnus X-1 stands as a crucial signpost, pointing the way toward potential answers. It is not merely the first black hole we ever found, it continues to be one of the most important we will ever study. Its story is not over. In many ways, it has only just begun. And so we look back up at the swan flying eternally across the river of the Milky Way. Buried within its graceful form is a point of utter darkness, a gravitational scar left behind by a star that died long ago. But that darkness is not an ending. It is a source of illumination. Cygnus X-1 is more than just an object. It is a testament to the power of human curiosity. It represents our relentless refusal to accept the universe as it appears to be, our insatiable drive to probe the shadows and question the impossible. Its discovery was a story of scientific perseverance, of bold new technologies, and of the courage to embrace an idea that seemed to violate common sense. It is a story that has inspired, and will continue to inspire, new generations of scientists, explorers and dreamers to look up at the night sky and ask their own profound questions. From a faint flickering signal in a rocket-borne detector to a cornerstone of modern physics, the journey of Cygnus X-1 mirrors our own journey of cosmic understanding. It is a constant, humbling reminder that the universe will always be more ingenious and more surprising than our imaginations. It taught us that the greatest wonders often lie hidden not in the bright blaze of 1,000 suns, but in a patch of perfect darkness, waiting patiently for us to find the right way to look. The ghost in the machine is now our guide, a cosmic lodestar, leading us ever deeper into the heart of the ultimate mystery.